Alright, let's go. Number 10. The Hubble Tension. Adam Rice and his collaborators at Johns Hopkins were doing routine calibration work. Their goal was to tighten the error bars on the Hubble constant, the number describing how fast the universe expands, using the same standard candle technique astronomers had used for decades. This was maintenance, not revolution. They were refining a well-known quantity by a few percent. The standard model of cosmology predicts one expansion rate, measurable in two independent ways. The local distance ladder uses Cepheid variable stars to calibrate Type 1a supernovae. The cosmic microwave background method uses the acoustic peaks in the early universe and evolves them forward through Nel-CDM. Both should return the same number within their uncertainties. That is the entire logic of a self-consistent cosmology. They don't return the same number. And every refinement makes it worse. Adam Rice and the SH0ES collaboration, published in the Astrophysical Journal Letters in 2022, volume 934, a local value of 73.04 plus or minus 1.04 kilometers per second per megaparsec. The Planck collaboration's 2018 results in Astronomy and Astrophysics, volume 641, give 67.4 plus or minus 0.5 from the cosmic microwave background. The disagreement now exceeds 5 sigma. Every proposed resolution has failed. Wendy Friedman's Carnegie-Chicago Hubble program used tip-of-the-red giant branch stars to bypass Cepheid crowding. Result, 69.8. Still incompatible with both. JWST observations by Friedman in 2024 confirmed the original Hubble Space Telescope Cepheids were not miscalibrated. Early dark energy models proposed by Vivian Poulin and Tristan Smith relieve the Hubble tension, but generate new tensions with matter clustering. Sound horizon modifications by Jose Bernal and colleagues fail to fit the baryon acoustic oscillation data. Local void explanations fail galaxy count tests. Either the two most careful measurement chains ever built are quietly wrong in different directions, or the theory underlying every cosmological calculation you have ever read is broken. The universe cannot be expanding at two speeds. So which of the two numbers, measured with the best instruments humans have, is lying? The next one is the reason those measurements matter at all. Number 9. The 1998 discovery itself. In the mid-1990s, two rival teams were racing each other. The High-Z Supernova Search Team, led by Brian Schmidt and Adam Riess, and the Supernova Cosmology Project, led by Saul Perlmutter at Berkeley. Both were measuring distant Type 1a supernovae. Neither team was hunting for something new. They were trying to measure how fast gravity had been slowing the expansion. The question was assumed to be how much braking, not whether braking existed at all. Standard cosmology in 1995 held that matter dominated the universe. Distant Type 1a supernovae should therefore appear brighter than a coasting expansion would predict, because gravity had been decelerating the cosmos for billions of years, packing distances closer than they otherwise would be. They appeared fainter. Adam Riess and colleagues published in the Astronomical Journal, volume 116, in 1998. Saul Perlmutter and colleagues followed in the Astrophysical Journal, volume 517, in 1999. Both teams found, independently, that Type 1a supernovae at redshifts near z equals 0.5 were roughly 25% dimmer than a decelerating universe permits. The result won the 2011 Nobel Prize in Physics, shared by Perlmutter, Schmidt, and Riess. Every prosaic explanation was tested. Intergalactic dust could dim distant supernovae, ruled out because dust reddens light and no reddening was observed. Evolution of the progenitor white dwarfs over cosmic time could bias intrinsic brightness, ruled out because spectra of nearby and distant supernovae match. Gravitational lensing biases, statistically negligible at those redshifts. Photometric calibration errors, checked exhaustively by both teams using different telescopes and different passbands. Nothing worked. What remained was a universe accelerating outward, powered by something no one could identify. The Nobel citation praised the discovery. It did not explain it. 26 years later, the mechanism behind the observation that reshaped cosmology has never been identified. You are living inside a scientific revolution whose founding result has never been closed. If two rival teams find the same forbidden result independently, does that make the finding more trustworthy? Or does it mean physics has been quietly missing something all of us have been standing inside? The next one is what happens when you look closer at the supernovae themselves. Number 8. The Type 1a dimming anomaly. After 1998, physicists went to work reconstructing dark energy's equation of state, the parameter W that determines whether dark energy behaves like Einstein's cosmological constant, like a slowly evolving field, or like something more dangerous. Eric Linder at Berkeley and colleagues built the standard parameterization used ever since. The goal was to pin W down and force it to name itself. If dark energy is Einstein's cosmological constant, W must equal exactly -1 across all cosmic time. Every major survey, SDSS, Wiggles, the Dark Energy Survey, should return -1 within their measurement bars. That is the null hypothesis of modern cosmology. The surveys return values close to -1, but never a clean mechanism supplying -1. And close, in physics, is where dragons live. The Dark Energy Survey Year 5 Supernova Analysis, published by the DES collaboration in the Astrophysical Journal Letters in 2024, volume 973, reports EBU equals -0.80 plus or -0.18 using supernovae alone. The value is pulled toward -1 only when combined with cosmic microwave background and baryon acoustic oscillation priors. Standalone, the supernovae prefer a milder acceleration than Einstein's constant provides. Every explanation is partial. Malmquist selection bias in distant samples, controlled for using volumetric cuts. Host galaxy dependence, mitigated using the mass step corrections developed by Mark Sullivan and colleagues, but not eliminated. Progenitor channel confusion between the single degenerate and double degenerate white dwarf merger pathways, still unresolved, still quietly haunting every result. Photometric standardization errors between telescope systems. The SALT-3 model reduced them but did not close them. The observation that gave us dark energy is not the same observation, run at higher precision. The signal is refusing to point cleanly at any specific physical mechanism, and it has been refusing for over 2 decades. If the supernovae themselves are quietly nudging away from Einstein's cosmological constant, while every combined analysis nudges back toward it, which of the two is the theory imposing its shape on the data? The next one is the mismatch that broke a generation of physicists. Number 7. The cosmological constant problem. In the late 1980s, Steven Weinberg, Nobel laureate for unifying the weak and electromagnetic forces, turned to a puzzle that had bothered him for decades. Quantum field theory, the most successful physical framework humans have ever built, predicts a specific vacuum. Empty space is not empty. It hums with fluctuating quantum fields, each carrying zero-point energy. Sum the zero-point energies of every quantum field up to the Planck scale. That sum represents the vacuum energy density of empty space. General relativity demands this energy gravitate. It must therefore contribute a cosmological constant, curving spacetime. The universe should either have instantly recollapsed at the Planck time or torn itself apart in an instant. It did neither, and we sit inside the discrepancy. Steven Weinberg's 1989 review, in Reviews of Modern Physics, Volume 61, page 1, laid out the disaster in full. The theoretical prediction exceeds the observed cosmological constant by a factor of roughly 10 to the power of 120. Not 120 times too large, 120 orders of magnitude too large. That is the largest disagreement between theory and observation in the history of physical science. Every attempted fix has quietly collapsed. Supersymmetry was proposed to cancel bosonic and fermionic vacuum contributions against each other, but the Large Hadron Collider has now ruled out supersymmetric partners up to energies above 2 TeV in Atlas collaboration results published through 2023, with no discovery. Anthropic selection via a string theory landscape, championed by Leonard Susskind, requires a multiverse we cannot test. Sequestering mechanisms proposed by Nima Arkani-Hamed and collaborators in Physical Review D in 2014 attempt to hide vacuum energy from gravity, but require fine-tuning of their own. Dynamical relaxation models by Peter Graham and colleagues face falsification tensions with cosmology. The vacuum inside your body, every cubic centimeter of empty space between the atoms of your hand, should, according to our best physical theory, contain more energy than the entire observable universe. It does not. No one knows why. If our best theory of matter and our best theory of gravity together produce the largest wrong answer in physics, which of the two is actually correct? The next one is a coincidence so precise it looks almost chosen. Number 6. The coincidence problem. Cosmologist Paul Steinhardt at Princeton, who had helped develop the theory of inflation earlier in his career, was working through the standard cosmological timeline in the late 1990s. He noticed something odd about when in cosmic history human beings had appeared to do the noticing. Dark matter and dark energy evolve differently as the universe expands. Matter density dilutes with volume. As space grows, matter thins. Dark energy density stays constant. That is what cosmological constant means. Over 13.8 billion years, their ratio should sweep from vast dominance of matter to vast dominance of dark energy, briefly crossing through parity. We are alive during the crossing. Present-day measurements from Planck 2018, published by the Planck Collaboration in Astronomy and Astrophysics, volume 641, place matter density at roughly 31% and dark energy at roughly 69% of critical density. Their ratio has been within an order of magnitude of unity only for the last few billion years, and will be within that range only for a few billion more. On cosmological timescales, we live inside a keyhole moment. Every explanation is uncomfortable. Anthropic arguments invoke a multiverse in which observers can only exist during eras that permit structure formation, an approach defended by Steven Weinberg in a 1987 Physical Review Letters paper, but requires a landscape of universes no experiment can reach. Quintessence models with tracker solutions, developed by Steinhardt and Ivaylo Zlatev in Physical Review Letters in 1999, ease the coincidence, but at the cost of new fields no one has detected. Cyclic universe models by Steinhardt and Neil Turok move the problem rather than solve it. Every human being who has ever asked the dark energy question has asked it during the one cosmic epoch in which the question is even interesting. Observers earlier or later would see a much simpler universe. Is the coincidence real physics, or is it just where we happen to be? And if it is just where we happen to be, what does happen mean at cosmological scales? The next one made every older problem on this list suddenly worse. Number 5. The DESI Evolving Dark Energy Hint. The Dark Energy Spectroscopic Instrument, mounted on the Mayall Telescope at Kitt Peak in Arizona, was designed to make the most precise map of the universe's expansion history ever attempted. The collaboration, led by Michael Levy at Berkeley Lab, measures the redshifts of tens of millions of galaxies and quasars to trace baryon acoustic oscillations across billions of years of cosmic time. The team was not trying to overturn Einstein. They were trying to measure him more precisely than anyone ever had. If dark energy is a genuine cosmological constant, its equation of state parameter W must stay locked at exactly -1 across every redshift bin. Any statistically significant deviation implies dark energy is something other than a constant, something that evolves. In April 2024, DESI reported deviation. The DESI collaboration released the first-year baryon acoustic oscillation results in April 2024. The headline result, combining DESI with the cosmic microwave background and Type 1a supernovae, evolving dark energy is preferred over a cosmological constant at between 2.5 and 3.9 sigma, depending on which supernova compilation is used. The parameter W appears to be less negative today than in the deeper past. Dark energy may be quietly weakening as the universe ages. Every conservative explanation has struggled to hold. Systematic issues in the luminous red galaxy sample at redshift Z near 0.7, investigated extensively without resolution. Tension between the Pantheon Plus, Union 3, and dark energy survey supernova samples that give slightly different preferences, itself a concern rather than a resolution. Correlations with the Hubble tension noted by Eleonora de Valentino and colleagues, suggesting the same underlying physics may be shifting multiple measurements simultaneously. Statistical fluctuation was possible in 2024, but the DESI Year 2 release in April 2025 reported the effect had grown, not weakened. If dark energy is evolving, the ultimate fate of the cosmos is not the cold, empty heat death that USCDM predicts. It could be a slow collapse. It could be an accelerating rip. It could be a smooth return to matter dominance. The ending depends on which way dark energy is going. If the largest galaxy survey in human history is telling us the biggest thing in the universe changes over time, what else that we have been treating as constant is quietly moving? The next one predicts an ending stranger than heat death. Number 4. Phantom dark energy. In 2002, physicist Robert Caldwell at Dartmouth College was mapping the parameter space of dark energy models. He was doing a categorization exercise, cataloging what values the equation of state W could mathematically take. He was not proposing that any of them describe reality. He was drawing a map. A cosmological constant has W equal to -1. Quintessence models have W between -1 and -1/3. Physicists had assumed W could not drop below -1 without violating the null energy condition, a basic assumption in general relativity that ensures energy always flows in physically reasonable directions. Caldwell noticed the math worked anyway. Robert Caldwell's 2002 paper in Physics Letters B, volume 545, introduced phantom dark energy, models with W below -1. The follow-up paper by Caldwell, Mark Kamiankowski, and Nevin Weinberg, published in Physical Review Letters, volume 91, page 071301, in 2003, worked out the consequence. If W is even slightly below -1, dark energy density grows over time instead of holding steady. Bound structures come apart at predictable moments before a final singularity. Current DESI constraints do not exclude phantom values. Every attempted refutation has fallen short. Quantum instabilities from the phantom field's negative kinetic term, pointed out by James Klein and colleagues in Physical Review D in 2004, suggest phantom fields should decay catastrophically through the vacuum. The instability rate may or may not matter on timescales relevant to us. Effective field theory descriptions by Nima Arkani-Hamd and collaborators show phantom behavior can be mimicked by more standard fields near a cosmological horizon, blurring the distinction. No one has ruled the models out cleanly. If dark energy is even mildly phantom, galaxy clusters are torn apart first, then galaxies, then solar systems, then planets, then atoms themselves. Caldwell's calculation, for one specific phantom value, placed atomic dissociation at roughly 22 billion years from now, well within the lifetime of a stable main-sequence star. Descendants living inside that timeline could compute the date on which everything comes apart. If the same equations that describe a gentle eternal expansion also describe a specific moment at which every bound structure in the universe unbinds, which of the two futures is the one we are actually in? The next one asks whether dark energy exists at all. Number 3. The void hypothesis. In the mid-2000s, cosmologists including George Ellis at the University of Cape Town and David Wiltshire at the University of Canterbury in New Zealand raised a quiet, contrarian objection to the entire dark energy story. What if the observed acceleration is not caused by an unknown energy? What if it is caused by where we happen to be sitting when we make the measurement? Standard cosmology assumes the universe is homogeneous on large scales, that any observer, anywhere, sees roughly the same average density. This assumption, the Copernican principle, underlies every calculation of dark energy from supernova brightness. Remove the assumption and the inference weakens. In 2013, evidence emerged that our local region may not be average. Ryan Keenan, Amy Barger, and Lennox Cowie, published in the Astrophysical Journal, volume 775, page 62, in 2013, evidence for what became known as the KBC void, an underdensity roughly 2 billion light-years across, containing our galaxy. The measured underdensity runs on the order of 30% below the cosmic mean. A structure that large is difficult to reconcile with standard structure formation in less dm, at reported probabilities well below 1 in 1 million. Every counter-argument has partially failed. Selection biases in the galaxy counts, investigated by multiple independent teams. The void persists. Wiltshire's Timescape Cosmology, published in Physical Review Letters in 2007, formalized how void inhomogeneity could mimic dark energy, but was criticized as producing wrong cosmic microwave background patterns. In late 2024, a team led by Wiltshire published reanalyses in monthly notices of the Royal Astronomical Society, arguing Timescape fits Pantheon plus supernova data marginally better than less CDM. The debate has not closed. Every distance in cosmology is measured relative to the assumption that our vantage point is generic. If it is not, If we sit inside a bubble of below-average density carved out by chance, then the entire dark energy inference could be an artifact of our address in the universe. If a discovery worth a Nobel Prize can be plausibly explained by the accident of where we evolved, how confident should we be about any distant measurement we have ever made? The next one goes further. It argues gravity itself is wrong. Number 2. Modified gravity versus dark energy. In 1983, Israeli physicist Mordechai Milgram at the Weizmann Institute was analyzing galaxy rotation curves, the flat velocity profiles of stars orbiting at the edges of spiral galaxies. He was trying to avoid postulating invisible matter. He proposed instead that Newton's second law itself modifies at very low accelerations, below a critical threshold, now called A0. Einstein's general relativity is our most tested theory of gravity, verified across 17 orders of magnitude in acceleration, from tabletop torsion balances to binary pulsars. It should describe gravity at every scale cleanly. When applied at galactic and cosmic scales, it requires 95% of the universe's contents, dark matter plus dark energy, to be substances that no laboratory has ever detected. Mordechai Milgram's original Monday paper appeared in the Astrophysical Journal, volume 270, in 1983. Jacob Bekenstein's relativistic extension, TVS, was published in Physical Review D, volume 70, page 083509, in 2004. More recent work by Konstantinos Skordis and Tom Zlaznik, published in Physical Review Letters in 2021, presents a relativistic Mond variant that reproduces both galaxy rotation curves and cosmic microwave background acoustic peaks, the second requirement historically the hardest for any modified gravity theory to satisfy. Every alternative has partial failures. Galaxy cluster dynamics still require unseen matter even in Mond, established by Douglas Clowe's bullet cluster analysis published in the Astrophysical Journal Letters in 2006. Gravitational lensing maps of the bullet cluster show mass offset from visible baryons in ways Mond struggles to reproduce. But FR gravity models by Wayne Hu and Ignacy Sawicki in 2007 fit expansion history without dark energy, while sidestepping some cluster problems. No single alternative theory fits every scale cleanly. Neither does nil-CDM. One of the two most confirmed frameworks in physics is quietly wrong. Either dark energy exists as an unknown substance filling every cubic centimeter of space around you, or gravity itself, the force holding your body to the Earth in this moment, obeys rules different from the ones we teach in universities. If gravity is the wrong theory, at what scale did we start being wrong, and how would we ever know? And the final one is the emptiest name in modern physics. Number 1. Why dark energy has no known particle, field, or mechanism. In 1998, when the accelerating expansion was announced, physicists began hunting for the responsible entity. Every previous major discovery in the Standard Model, the electron, the photon, the W and Z bosons, the Higgs, had produced experimental programs and candidate particles within a decade of the theoretical prediction. Dark matter, though undetected, has at least dozens of well-defined candidate particles. Dark energy is by mass energy content the largest thing in existence. It comprises roughly 68% of the total energy of the observable universe. A phenomenon that dominant in a physics as mature as ours should point somewhere. In 26 years, it has pointed nowhere. According to the Planck Collaboration 2018 Results in Astronomy and Astrophysics, volume 641, page A6, dark energy accounts for 68.5% of the universe's energy density. No accelerator experiment has produced a dark energy quantum. No astronomical observation has isolated a dark energy field beyond its bulk gravitational effect. No laboratory measurement of vacuum energy density has ever matched the cosmological value. The gap between what we can name and what we can measure has not narrowed since the Nobel citation in 2011. Every candidate has quietly failed. Quintessence fields require ultralight scalars with masses on the order of 10 to the power of minus 33 electron volts, undetectable by any existing instrument. Chameleon and symmetron field models by Justin Corey and Amanda Weltman, published in Physical Review D in 2004, evade fifth force constraints only by making themselves untestable in the regimes where they matter. Vacuum energy from quantum field theory returns the 10 to the 120 disaster. Modified gravity moves the problem to space-time geometry. Cyclic and bouncing cosmologies invoke earlier epochs we cannot observe. No candidate has ever crossed cleanly from mathematics into measurement. 2/3 of everything is a placeholder name for an equation term. The energy accelerating you outward from every other galaxy, at this moment in the room you are sitting in, has no known constituent. When physicists write nil CDM, the lambda is not an answer, it is an admission. If we cannot even name what the majority of the universe is made of, what does it mean to say we understand the universe at all? Every anomaly on this list sits not at the fringes of physics, but at its center. The Hubble constant, the vacuum, the equation of state, the fate of the cosmos. These are not exotic edges. They are the load-bearing walls of modern cosmology, and each one has a crack running through it. The universe is not confused. It is behaving consistently, according to rules it has never told us. We are the ones filling the silence with names. If you want to see more videos like this, click the video on screen now.